go. Okay, so these are the objectives for the second exam. Chapter 5 is concerned about z-scores and location. So you should know the formula for a z-score and what is measured by the numerator and the denominator. And know the represented location of z-score values on a normal distribution. Know how to find out the z-score corresponding to a particular x score or value, and as well as the opposite. If given a z-score, well, that's what it says. Never mind. So be able to do it both ways. So if given a z-score, be able to tell the raw score, or if given a raw score and a mean, be able to figure out the z-score. And then using z-scores, be able to find out the proportion or probability of that on a normal distribution. So chapter 6 is about the standard error of the mean and why we use the standard error of the mean instead of just a regular standard deviation. So know how to calculate that and know what it is measuring. So basically the standard error of the mean is like the standard deviation of a sampling distribution. So if you took a bunch of samples and plotted them on a graph, you would calculate the standard error instead of the standard deviation to measure the average error. So chapter 7 is hypothesis testing, and you need to know what type 1 and type 2 errors are, what affects type 1 and type 2 errors, how to set up null and alternative hypotheses, definitions of alpha level, critical region, and steps of hypothesis testing, and when to make decisions about rejecting the null or failing to reject the null hypothesis. So the standard normal probability distribution is a regular normal curve distribution, and z-score distributions, which is a standard normal probability distribution, all have the same mean and standard deviation. Individual scores from different distributions can be directly compared. That's why we use them, so we can compare apples and oranges. It has a mean of 0 and a standard deviation of 1. A z-value is the sign distance between a selected value and a designated x, and the mean, which would be mu, divided by the standard deviation, sigma. So there is the formula for a z-score right here. So z-scores and location. A score of x equals 53, for example, may be a relatively low score or an average score or an extremely high score, depending on the mean and standard deviation for the distribution from which the score was obtained. So if the raw score is transformed into a z-score, however, the value of the z-score tells you exactly where the score is located relative to all the other scores in the distribution. So a z-score of +1 is 1 standard deviation above the mean, and a z-score of -1 is 1 standard deviation below. So z-scores, the sign of the z-score, positive or negative, identifies whether the x value is located above the mean or below the mean. The numerical value of the z-score corresponds to the number of standard deviations between the score x and the mean of the distribution. A z-score that is located 2 standard deviations above the mean will have a score, sorry, not a z-score, will have a z-score of +2. And a z-score of +2 always indicates a location above the mean by 2 standard deviations. So a distribution has a standard deviation of 6. Describe the location of each of the following z-scores in terms of relative position to the mean. For example, +1 is a location that is 6 points above the mean. So the heights of students in this class form a normal distribution with a mean of 68 and a standard deviation of 2 inches. What is the probability of randomly selecting a student who is taller than 6 feet, 72 inches? First, you would just calculate the z-score. So 72 minus 68 divided by 2, and that would give you a z-score of +2, meaning that person is 2 standard deviations above the mean. So then you look up the probability on your normal curve table, and you use the left-hand side to find a z-value of 2, and then go over to the smaller portion column, and that's where this 0.20228 came from, which is also 2%. So the probability of randomly selecting one student who's taller than 6 feet, if the mean is 68, is only about 2% chance. And I think that probably has to do with the amount of girls that we have in our class versus boys. So shorter than 64 inches, you would do the same thing, but now it's 2 standard deviations below the mean. So what would be the probability without looking at your table? Exactly, because your table only gives you absolute values. So exactly the same. So here is a picture. The top one is a normal probability table without probabilities, or a normal curve, and has a mean of 0, standard deviation of 1, and then a population of scores, and this has a mean of 100, a standard deviation of 10, and you can transform that into a population of z-scores, which would then have a mean of 0, standard deviation of 1. So find out what z-score values is the closest to the mean if the mean is 80 and the standard deviation is 2. Which one of these would be the closest to the mean? Mm-hmm. But it doesn't really matter. The sign. Which one of them would be the closest? Yes. Yeah. So negative 0.5 will always be closer to the mean, regardless of what the standard deviation is, than -1 or 2 or 1, +1. So SAT scores for the combined verbal and quantitative test at the UT have a mean of 1,000 and standard deviation of 200. What is the percent of the distribution that will be between a score of 800 and 1,200? So the first step here is you need to calculate z-scores for both 800 and 1,200, which they are the same. So the percent of the distribution that's between these, you would look up z score of 1 and then go over to the mean to z column and then add that value or multiply by 2. It's the same value. Add it together. And that would give you about approximately 68% of the distribution would be between a score of 800 and 1,200. So just keep in mind that the standard normal table, all of the probabilities add up to 1. 1 is the entire area underneath that curve. So if you get a value that's higher than 1, you did something wrong. So the basic z-score definition is usually sufficient to complete most z-score transformations. However, the definition can be written in mathematical notation to create a formula for computing the z-score for any value of x. This is a generic formula. So if z equals 1.5 for a population with a mean of 80 and a standard deviation of 6, what is the x, the score, the raw score? So here you're just rearranging this formula to isolate x on the right-hand side. So you would take your z-score, multiply it by your standard deviation, and then add your mean, mu, to the other side. So I took 1.5 times 6, our standard deviation, and then added our mean to it. And so a z-score of 1.5 corresponds to a raw score of 89. If a population has a mean of 60 and a standard deviation of 5, what is the z-score corresponding to x equals 70? So here you would just use the formula as it was written on the last slide, and it would be a positive 2. So if mu equals 50, you have a score of 40. Which value for the standard deviation would give you the highest position in the class distribution? 2, 4, 6, or 8? So if you can't just like conceptually look at this and think about it, the easiest way to figure it out is substitute, do 4 equations with these 4 different standard deviations. What do y'all think would give the highest position in the class? 2, 4, 6, or 8? No takers? It's going to be 8 because the score is 10 points below the mean, right? 40 minus 50 is negative 10. Standard deviation of 8 puts you at 1.25 standard deviations below the mean, which will be closer than all of these other options. So basically just subtract the top. Just do the numerator, figure out what that difference is, and then look at your options for your standard deviations. So whatever is closest to that difference in the numerator will put you in the highest position.
So by highest, you mean the closest to the mean?
Exactly.
So you'd want the standard deviation
The lowest standard deviation.
Okay.
Yeah, exactly. Okay, so a distribution of scores has a mean of 60 and a standard deviation of 5. What raw score corresponds to a z-score of plus 2? So you would work backwards like the first example on the last slide, and you would multiply 2 by 5 and then add 60 to it, and that would give you 70. And then if you wanted to work the other direction, what z-score corresponds to a raw score of 70. Obviously, you should know this because it's right there, plus 2. So the fact that z-scores identify exact locations within a distribution means that z-scores can be used as descriptive statistics and as inferential statistics. As descriptive statistics, z-scores describe exactly where each individual is located in the distribution. As inferential, z-scores can determine whether a specific sample is representative of its population or is extreme or underrepresented. Meaning, you can use your z-score formula to test hypotheses if you know your population standard deviation and hypothesized population means. It's also possible to calculate z-scores for samples. So the definition of a z-score is the same for either a sample or population, and the formulas are also the same except that the sample mean and standard deviation are used in place of the population mean and standard deviation. So here you have S for the sample standard deviation instead of sigma, and here you have the sample mean instead of mu, the population mean. So using z-scores to standardize a sample also has the same effect as standardizing a population. Specifically, the mean of the z-scores will be 0 and the standard deviation of the z-scores will be equal to 1, provided that the standard deviation is computed using the sample formula, dividing by n minus 1 instead of just n. And that was all of Chapter 5. Chapter 6, Probability in the normal distribution. If a vertical line is drawn through a normal distribution, several things occur. The exact location of the line can be specified by a z-score, and the line divides the distribution into two sections. The larger section is called the body, and the smaller section is called the tail. So B is the body, and C is the tail, and then D is mean, whatever the mean may be, to Z. Well, the mean is going to be 0 if it's a z-score, but so to find the probability corresponding to a particular score, or x value, you first transform the scores into z-scores, then look up the z-score in the table and read across the row to find the appropriate probability or proportion. To find the score, x value, corresponding to a particular proportion, you first look up the proportion in the table, meaning the tail, right? And then read across the row to find the corresponding x z-score, and then transform the z-score back into an x value. So here, if we wanted to know what cutoff for an A and a B should be, and we want to make the top 10% get an A, we would look in the smaller portion or the tail portion column for a value of 0.1, and that would cut off 10% in this section, and we would read off what z-score corresponds to that, 0.1% in the tail, and then transform that back into a raw score. So here you go. So this is what I was just describing. 10% in the tail, 90% in the body. You'd figure out what that z value is and then change it back into a raw score. Later when you're doing two-tailed tests, the z value that you look up, say you have an alpha level of 0.05, you would look in the tail for 0.05 if it was a one-sided test, a one-tailed test. The z-table always puts everything all on one side. So if you wanted to do a two-tailed test at 0.05, you would need to divide 0.05 by 2 and then look in the tail or smaller portion column for 0.025, and that will give you your z-score boundaries. So the general goal of inferential statistics is to use information from a sample to reach general conclusions or inferences about an unknown population. If the sample has a high probability of being obtained from a specific population, then the researcher can conclude that the sample is likely to have come from that population. If the sample has a very low probability of being obtained from a specific population, then it's reasonable for the researcher to conclude that the specific population is probably not the source of the sample. Once this distribution is identified, then a z-score can be computed for each sample mean. The z-score tells where the specific sample mean is located relative to all the other sample means, and the probability associated with a specific sample mean can be defined as a proportion of all the possible sample means. So this is talking about the distribution of sample means. Because the distribution of sample means tends to be normal, the z-score values obtained from a sample mean can be used with the standard normal or unit normal table to obtain probabilities. The procedure for computing z-scores and finding probabilities for sample means is essentially the same as we used for individual scores, except now you're going to be using the standard error of the mean, which is the standard deviation divided by the square root of the sample size. So the standard error of the mean is defined as the standard deviation of the distribution of sample means, and it is a measure of the standard distance between a sample mean and a population mean. So if this "and," the last part of the sentence, was written in symbols, using symbols, it would be the difference between sample mean M, capital M, and population mean mu. Keep that in mind. Thus, the standard error of the mean provides a measure of how accurately, on average, a sample mean represents its corresponding population mean. So all the standard error of the mean is doing is standardizing all of our samples that we've taken, if we took multiple samples, and giving us an average of the error, the sampling error. The magnitude of these standard errors is determined by two factors: the standard deviation and the sample size. The population standard deviation, which measures the standard distance between a single score and the population mean, and when you divide it by the square root of the sample size, it standardizes it. So the standard deviation provides a measure of the error that is expected for the smallest possible sample when n equals just 1. As the sample size increases, it's reasonable to expect the error should decrease. So the larger the sample, the more accurately it should represent its population. The formula for the standard error mean reflects the intuitive relationship between standard deviation, sample size, and error. As sample size increases, the error decreases. As sample size decreases, the error increases. At the extreme, when n equals 1, the error is equal to the standard deviation. So as you're making your denominator smaller, your end product gets larger. As this gets bigger, this gets smaller, the standard error. So the only time you will use standard error of the mean is if you're given some type of problem like this, where you're told a random sample of, here's 4 scores are selected from normal population with a mean of 80 and a standard deviation of 20. So like previous examples where we calculated the probability of a specific score in a population, you would just use your standard deviation as your denominator for calculating your z-score. Whenever you're told a sample was taken and how likely would it be that you could take another sample of that size and get the same result or same mean, then you're going to use your standard error of the mean. as your denominator in your z-score formula. So here, the standard error of this distribution of sample means would just be the square root of n under 20. So 20 divided by the square root of n, your standard error of the mean would be 10. So chapter 8, hypothesis testing. The general goal of a hypothesis test is to rule out chance or sampling error as a plausible explanation for the results from a research study. Hypothesis testing is a technique to help determine whether a specific treatment has an effect on an individual in the population. And it doesn't necessarily need to be a treatment. Just keep that in mind. It could be something other than an actual treatment. Is the status quo still the status quo? Are UT students on average have a higher IQ than Texas State students? So you wouldn't have any treatment, but you could still compare the means and test it. Hypothesis test is used to evaluate the results from a research study in which a sample is selected from the population, the treatment is administered to the sample, and after treatment, the individuals in the sample are measured. That's normally how it goes. If the individuals in the sample are noticeably different from the individuals in the original population, we have evidence that the treatment has an effect. However, it is also possible that the difference between the sample and the population is simply sampling error. So that means that you just happen by chance to select people from your normally distributed population that were outliers or extreme values. So they were out here instead of being in the center, right? And the purpose of hypothesis testing is to decide between two explanations. Did the difference between the samples and the population, can it be explained by sampling error, that there does not appear to be a treatment effect, the result is not significant, or the difference between the sample and the population is too large to be explained by sampling error. There does appear to be a treatment effect. The result is significant. So this high probability values, if HO is true, would give you a non-significant result. These in the tails, if your z-score is way out here, then it's an extremely low probability if the null hypothesis is true. And the hypothesis test is always testing the null hypothesis. We never test the alternative. If we reject the null hypothesis, that means we have found evidence to say that it is very unlikely that the null hypothesis is true, not that it isn't true, but it's just very unlikely. So, what is the null and alternative hypothesis? What's an alpha level? What describes the critical region? And what are the 4 steps to conduct hypothesis testing? So, step 1, state the null hypothesis and select an alpha level. The null hypothesis, H sub O, should be sub O, not large O, always states that the treatment has no effect, no change, no difference. Basically the status quo, whatever is already out there. According to the null hypothesis, the population mean after treatment is the same as it was before. The alternative hypothesis is everything else. So if you have a two-tailed test, your null hypothesis would be, say your population mean is 80, your null hypothesis would be mu equals 80. Your alternative hypothesis would be everything other than that, which would be mu does not equal 80. If it's a one-tailed test, you're going to need to look at the wording of the question to find out whether it's expecting an increase, and like say It's a weight loss treatment, and we're expecting a decrease in weight. So your null hypothesis will be mu equals 100, I don't know. Or mu is greater than or equal to 100. And then your alternative would be what you're expecting, that mu is less than 100. You're expecting decreases in weight. So in a directional test, your alternative hypothesis greater than or less than arrow will point in the direction on the standard normal table where you're going to be looking for your critical region. So if the alternative hypothesis says that they should lose weight, it should be less than 100, then you're going to be looking for your critical region on the left side, in the left tail. The alpha level establishes a criterion or cutoff for making a decision about the null hypothesis. And it also determines the level of risk of a type 1 error you're willing to make. So if you select an alpha of 0.05, you're willing to be wrong 5 times out of 100. If you select an alpha of 0.1, you're willing to be wrong 10 times out of 100. So it's based on whatever you choose. In this class, you'll usually be told what the alpha is. So just keep in mind that the alpha level is connected to the type 1 error rate. So 1.96, a z-score of 1.96 is an alpha level of 0.05. 2.58 is alpha of 0.01, and 3.3 is 0.001. So then the next step in hypothesis testing is locating the critical region. The critical region consists of outcomes that are very unlikely to occur if the null hypothesis is true. That is, the critical region is defined by sample means that are almost impossible to obtain if the treatment has no effect. The phrase almost impossible means that these samples have a probability, p, that is less than the alpha level. So if you got 1.96, your probability of that occurring is 0.05. It's your alpha level if you're right there at 1.96. If you're over here, it's something less than 0.05. That makes sense? Compute the test statistic is the third step. So the test statistic in this chapter is a z-score, and it forms a ratio comparing the obtained difference, which is the numerator, between the sample mean and the hypothesized population mean over the amount of difference we would expect without any treatment effect, or the standard error. So, step 4 is the conclusion. You make a decision about whether to reject or fail to reject. A large value for the test statistic shows that the obtained mean difference is more than would be expected if there is no treatment effect. If it is large enough to be in the critical region, we conclude that the difference is significant or that the treatment has a significant effect. In this case, we reject the null hypothesis. If the mean difference is relatively small, then the test statistic will have a low value. In this case, we conclude that the evidence from the sample is not sufficient to determine that the null hypothesis is not true. So there we would fail to reject the null hypothesis. And here's an example. If it is expected that the treatment will make a difference for individuals in a population which is known to have a mean of 50, the results will be examined using a two-tailed test. What's the null hypothesis? So in this example, the key word here is difference. It doesn't say anything about increase or decrease or what kind of treatment it is. So that keyword right there will tell you that it's a two-tailed test, even though it says it's a two-tailed test. So with two-tailed test, your null hypothesis is always going to be mu equals whatever the status quo is, which for us, in this example, it's 50. The alternative hypothesis would just be mu does not equal 50. So errors in hypothesis tests. Because the hypothesis test relies on a sample, and because sample data are not completely reliable, there's always the risk of that misleading data will cause the hypothesis test to reach a wrong conclusion. So there's two types of errors. A type 1 error occurs when the sample data appear to show a treatment effect when in fact there is none. There is no effect. In this case, the researcher will reject the null hypothesis and falsely conclude that the treatment has had an effect. Type 1 errors are caused by unusual, unrepresentative samples. Just by chance, the researcher selects an extreme sample with the results that the sample falls in the critical region, even though the treatment has no effect. The hypothesis test is structured so that type 1 errors are very unlikely. Specifically, it's the probability of a type 1 error is equal to the alpha level, whatever the alpha level is set at, 0.05, 0.01. Type 2 errors are the opposite. Occurs when a sample does not appear to have been affected by the treatment, when in fact the treatment does have an effect. In this case, the researcher will fail to reject the null hypothesis and falsely conclude that the treatment does not have an effect. Type 2 errors are commonly the result of a very small treatment effect, as well as a very small sample size. Although the treatment does have an effect, it's not large enough to show up in the research study, or your sample size is so small you don't have enough power to detect that effect. I don't think he's not going to be testing on power, so just keep in mind that sample size does have an effect on whether or not you'll be able to see a treatment effect. So here is a cool table. So HO is true, there's no effect. You retain HO and you've made a correct decision. If HO is true and there's no effect and you reject HO, you've made a type 1 error. On the opposite side, an effect does exist and HO should be rejected, but you retained it. That would be a type 2 error. And then if you actually did reject it, that would be a correct decision. Directional tests. When a research study predicts a specific direction for the treatment effect, increase or decrease, it's possible to incorporate the directional prediction into the hypothesis test. The result is called a directional test or a one-tailed test. A directional test includes the directional prediction in the statement of the hypotheses and in the location of the critical region. So if the original population has a mean of 80 and the treatment is predicted to increase the scores, then the null hypothesis would state that after treatment, you would expect that the mean would be less than or equal to 80. So the alternative hypothesis would be mu is greater than 80. And that greater than arrow would be pointing into the positive direction of the normal curve table. So the entire critical region would be located in the right-hand tail of the distribution because large values for the mean would demonstrate that there is an increase and would tend to reject the null hypothesis. So simple random sampling. A sample is selected so that each item or person in the population has the same chance of being included. The reasons why we sample in time, it's expensive if we wanted to sample everybody in specific populations. It's sometimes physically impossible. Sometimes it can be very destructive, like auto testing, cars, crash testing. They completely kill the car. And a lot of the times, a sample is enough information to make some kind of determination. And sampling error is the difference between a sample statistic and its corresponding population parameter. So sampling error, in terms of means, would be the sample mean, the difference between the sample mean and the corresponding population mean. So big M minus mu is your sampling error. Standard error of the mean. What is the standard error of the mean? It's also called the standard deviation of the sampling distribution, and it is the difference in the population mean and the sample means. So here, multiple samples were taken. So it's the difference between the population mean and all of the possible samples that could have been taken from that population. And here's the formula. The standard deviation of the population divided by the square root of the sample size. Here is an example. A random sample of 300 students are selected for an experiment. The result of the experiment shows that the sample mean of 30 and the sample standard deviation is 25. What is the sample standard error of the mean? So here, to answer this question, you do not need to know the sample mean. It does not matter. All you do is divide 25 by the square root of 300, which gives you a sample standard error of the mean of 1.44. Here's another example. Nike's annual report says that the average American buys 6.5 pairs of sports shoes. Shoes, not shows. Per year. Suppose the population standard deviation is 2.1 and that a sample of 81 customers will be examined next year. What is the probability that the sample mean is between 6 and 7 pairs of sports shoes? What is the probability that the difference between the sample mean and the population mean is less than 0.25 pairs? So first you calculate the standard error of the mean, which is the population standard deviation, 2.1, divided by the square root of your sample size of 81, and that gives you 0.233. So now that you have the standard error of the mean, you can calculate the z-score for 6 pairs of shoes. So 6 minus the mean of 6.5 divided by the standard error of the mean of 2.33 will give you a z-score of negative 2.15. Then you calculate the z-score for 7 pairs of shoes. And that gives you a positive 2.15. And then the probability of falling between the mean and z equals 0.4842. So 4842 plus 0.4842 equals 0.9684, or about 97% of the population would buy between 6 and 7 shoes. So if you wanted to know the probability of 6.25 pairs of shoes and 6.75 pairs of shoes, you would just do it again using the same standard error of the mean, but then changing your mean value. And that would give you the probability of falling between 1.07 and negative 1.07 is about 72%. So here's another one. A typical family spends on an average of $160 a month on food with a standard deviation of 30. If the family food bills form a normal distribution, what is the probability of finding a family that spends less than 115? So here, compared to here, so here it's asking the probability of selecting a sample mean, selecting a sample that has a mean between here and here. Here, it's asking the probability of finding a single family that spends less than this amount. So you wouldn't use the standard error of the mean on this question. You would just use the actual standard deviation. So it'd be 115 minus 160 divided by the standard deviation, 30, and that would give you a z-score of negative 1.5. And a z of negative 1.5, the probability of selecting a family that spends less than 115 if the population mean is 160 is about 6%, almost 7% chance of selecting a single family that spends less than that. So here on the test, read these types of questions very carefully. Find out if it's asking like the probability of one score, or the probability of one family, like in this example, or the probability of selecting a sample of a specific size, because that's going to determine whether you use the standard error of the mean as the denominator or just the standard deviation as the denominator. So here's an error type example. Even if a treatment has an effect, it is still possible to attain a sample mean that is very similar to the original population mean. What outcome is likely if this happens? So your treatment worked, there is an effect, but you obtained a sample mean that is really close to the original population mean, or the hypothesized population mean. What type of error would that be? Type 1 or type 2? Yes. Type 2 error. So you would fail to reject the null when there really wasn't a treatment. There was a treatment effect. And that's it.